start with the GaN diode presentation on the GaN diode, followed by the impart diode, then the tapat, then the Barrett, followed by MESFET, gallium arsenide FET, and finally the HEMT. So beside each diode that we've indicated here are the areas that we majorly focused on. So like, for example, with the Barrett diode, I'm sure the person who will be presenting it will be focusing more on the injection and transit time without the avalanche. So like for my case, I'll be focusing more on the negative resistance and the others that will come along. So the two pictures on top here are the reference materials that we've used. So everyone who will be presenting here has somehow used any of these books, obviously, plus others that they might share along the way. So in case you guys will need these books, I'll just send it to the class rep, then you might get them alongside with the presentation. So I'll be presenting the GaN diode. So this is the outline that I followed. So we'll be talking about the basics of the GaN diode. From the basics, we'll derive the equivalent circuit, then the two-valley theory, because the two-valley theory and the GaN effect are the key components, not necessarily components, but the content behind the GaN diode. Then the characteristics of the GaN diode, how the GaN effect occurs. That's the basis of the characteristics of the GaN diode. And finally, the applications of GaN diode. Then I let the other person present. So we'll start with the basics of the GaN diode. So as you can see here, a GaN diode is a passive semiconductor device. By passive, we always mean that it's a component that does not generate or amplify the power in the circuit. Yeah, so GaN diode can be fabricated from the following compounds. That's the gallium arsenide, indium phosphide, alongside with these other component. Yeah, this chemistry stuff is juice. So the process of manufacturing a GaN diode for this matter is the epitaxial process that we learned in first semester of fourth year, the epitaxial process, the epitaxy process. So yeah, through that, if you can be able to create that one for yourself, then you can be in a position to have yourself a gallium arsenide diode for yourself. So these are the basics of the GaN diode. So it was invented by J.B. GaN in 1962. I don't remember the exact labs, but I had read about the labs, but I didn't indicate it here. So as you can see, this is just a repetition of what I had said earlier, the gallium arsenide, indium phosphide, and all those. So if you go to point number 4 here, we have GaN diode offers a negative resistance characteristics. Yeah. So this is actually the basis of operation of a GaN diode. We'll talk about it later when we get to that point. And again, the last point here, the GaN diode works based on GaN effect. Further, this one too, we'll talk about it towards the end of the slides. So this is a structure of GaN diode. As you can see, it's composed of an active layer, that's the N superscript plus. Yeah. So what this essentially means, the ends, the edges is a highly doped N type. So it has a like high concentration of like the atoms. Yeah. Then the N at the middle here, that's like a moderately doped region. So then this is the symbol of a GaN diode. The way a normal diode would have like this straight line and this triangle here up to this point here. So for GaN diode, it's like a mirror of one of a normal diode. Because if you place a mirror line somewhere here, it will come up with this this symbol here. So this is the structure of a GaN diode. As you can see, it's composed of a ceramic housing at the edges. We have a gold wire, the dopant side, which is the ends here. So here we form like kind of like a junction, a layer in that matter. So this is what is composed of: a semiconductor layer, the metallic contacts, gold wire, ceramic housing, and heatsink. So through this, what is composed of, we can derive an equivalent circuit. So this is a construction of a gun diode. It like kind of like built on this. I think from this one we can go to the okay. It's our two. So this is the construction of a gun diode. This is like from one of the textbooks that I had seen. So we won't go into much details concerning this symbol here, but things like the length and the length mostly won't be touching on it because it's like a foundation for what the entire group will be building on. So, so as you can see at the construction of GaN diode, the basic structure of a GaN diode consists of the N-type gallium arsenide semiconductor with region of doping. So although there is no junction like in the normal diodes, the ones that the ones that we're used to, there is a positive and the anode and the anode and the cathode. So that's the with reference to okay. So the GaN diode are grown epitaxially out of the gallium arsenide or indium phosphide. I think this is what I've repeated severally by now. So after that, you can for all these parts that you've seen here, the ends and these are the diagram here. These are the explanations that we have. So like if we can see the semiconductor layers, the ends, yeah, I think it's the regions of highly doped, less doped, and like moderately doped regions because that's the basis of the carriers. So to effect current flow. So then there is the metallic contacts. The metallic contacts, we had it here, up here. So let me just go back to it. It's the yellow part, That's the metallic contacts. Then the gray part is the ceramic contacts. Yeah. So okay, I think you are here. So the metallic contacts. So as you can see from these metallic contacts, these are ohmic contacts placed at the both ends of the semiconductor structure to ensure good electrical conductivity. So it contacts. So some a thing that we know about contacts is we always have some sort of resistance with each contact, and since there are two on both sides, there's some sort of capacitance in it. So that one will model when we are deriving the equivalent circuit of the GaN diode. So as you had seen earlier, I'll just scroll back. There is a there is a gold wire here, so that's what we're talking about it right now. So the gold wire, it connects the semiconductor to the external circuit. So any other circuit that might need to be connected to the GaN diode will be connected through the gold wire. So then there is the ceramic housing. So the ceramic housing, as the word housing states, it like kind of like protects something, yeah. So it like protects the GaN diode. It encloses the GaN diode. So then there is a heatsink, as you had seen up there. So you might ask yourself, why do we need a heatsink in a diode? So the reason is where gallium arsenide during conduction, gallium arsenide generates a lot of heat, and again, gallium arsenide from its properties, it's that it's a poor conductor of heat. So it tends to dissipate heat slowly. So in to cater for that so much heat that's generated, we need a heat sink, and normally these heat sinks will be made of materials that have high heat conductivity, thermal conductivity for that matter. So I think elements like copper and aluminium are the best suit for the heatsink here. So yeah, so most of the heatsinks that are used in this area are either aluminium or copper. Yeah. So as I had said, the equivalent circuit system. So this is the equivalent circuit of the GaN diode. This is how it can be modeled. I told you because of the two metallic contacts, there's some sort of capacitance, there's some sort of resistance pair because of the contacts. So this, I think everyone can see this clearly. Yeah? Or should I zoom it? Okay. Yep. So this is the equivalent circuit, as you can see. It's indicated with the subscripts for you to understand it properly. So the C subscript P, that's the package capacitance, which is due to the metallic caps that I had shown you, the ones in yellow. If I can scroll back and just see it. So this is the basis of our equivalent circuit. So you can see you have the contacts there, the gold wire, ceramic, and everything. So Yep. So that's the C subscript P. Then the L subscript P is the package inductance, which again is due to the two cups, the yellow area that I'd shown you in the diagram. So then we have the C subscript J. Now, since this is the junction capacitance, which is due to the two cups, and I think, okay, no, just leave it at that. So the R subscript J, which is this one here, which is in parallel with the C subscript J, that's the junction resistance. This is actually modeled from, I'll just scroll back where it's modeled from. These layers here, is the three layers here between the ends here. That's what is responsible for the capacitance, the C subscript J and the R subscript J, the junction resistance. So then finally you have the ohmic resistance. This is the due to the contacts, the resistance due to the contacts. As we had said earlier that the two contacts here, the one in yellow is responsible for the capacitance and the inductance, the C subscript P and the L subscript P. So since these are metallic structure and it conducts, there's always some sort of resistance that comes with it. So that's modeled as the ohmic resistance here. So far, I think we are at the same page, guys. Hello. Okay. So the two valley theory. So this is actually, it forms the basis of operation of the gun diode. So that from, if you can remember from physical electronics, I think we had such a structure like this one. Not a structure but a diagram like this one, where you have the conduction band, the valence band, and the energy gap. So as you can remember, for conductors, I think the valence band and the conduction band tends to like overlap, yeah. But with semiconductors, they don't overlap. There's always some sort of energy gap that needs to be overcome. So for this model, the RWH theory or two valley theory, yeah, it was developed by it was coined by these two. Actually, I don't know if it's three guys. Really. So it's Ridley, Watkins, and Hilsum theory. So the basis of this theory, as you can see, we have like, okay, if I can zoom in, we have like lower energy on the conduction band and the upper lower valley and the upper valley. So this theory suggests that in the conduction band, this one above here, yeah, it suggests that in the conduction band there are two regions where carriers, in this case the carriers are electrons, exist based on their effective masses. So in the first valley, this is the lower valley here, the electrons have lower effective mass, and with lower effective mass we always have high mobility, because if we had like two electrons, one has, let's say, a mass of 3 and the other one has a mass of, let's say, 8, the one with a mass of 3 kind of has a higher mobility than the one with higher mass. So and the second one is the upper valley, as you can see from the diagram where my cursor is at the moment. So electrons in this region, or in this valley, have a higher effective mass, and with higher effective mass there is lower mobility. So since we're talking about electrons, and as you can know, current, the definition of current is the flow of charges. Yeah, in this sense, it's the electrons. Since we have lower mobility, the current flow here will be much lower compared to the lower valley because of the difference in mobilities. So another thing that I need to point out is at the upper valley, this section here, it's normally unoccupied at low electric field, because the basis of operation of gun diode is application of electric field, voltage current relationship, as we will see it later. What I'm trying to say is that if you apply much voltage to gun diode, there's a tendency of the current not increasing, because if you can remember from the V equals IR relationship, for any circuit, if we have a constant value of R, if we increase the value of voltage, let's say from 10 to 20, and the value of current will increase to retain that relationship. But in this case, you'll realize that as the voltage increases, the current does not increase. As a matter of fact, decreases. The reason why I'll explain it later, but just have that in mind because it's part of the basis of the gun diode. So as I said earlier, that normally this region here, the upper valley, is normally unoccupied at low electric fields because the valley requires so much energy. So obviously because of the, like in this case, the 0.36 electron volt, we need to overcome that energy. That's why we don't have much carriers at normal conditions. So if we can just read through these, is the two volume model suggests that there are two regions in the conduction band which charge carriers can exist. Yeah, so these regions are called valleys and are designated the upper valley and the lower valley. So according to the Ridley-Watkins-Hillsum theory, electrons in the lower valley have lower effective mass. So in this case, from the text that I used, is 0.068 and consequently higher mobility. So as I think you can see the relationship from the examples that we've indicated here. So in the upper valley, which is separated from the lower valley by potential of 0.36 electron volts. So this is the energy that needs to be overcome for an electron to move from lower valley to the upper valley. The electrons have much higher effective mass. That's a 1.2 compared to the one that we had in the uh, lower value of 0.06. So if you can see, that difference is actually significant. So and obviously with the high effective mass comes the lower mobility. That's like the 180 centimeters. Yeah. Uh, so the transfer of electrons from the lower conduction valley to the upper conduction valley depends on the electric field applied and a threshold that needs to be met. So as you apply the electric field, the electrons in the lower valley will tend to gain some energy. So it will gain some energy until some certain point where, if the threshold is overcome, no, I think the threshold in this case will be the 0.36. Anything above the 0.36 electrons volt, the electrons will start moving from the lower valley to the upper valley. So I think next that we are going to discuss from here is the electrons transfer mechanism, because you realize that we need to transfer the electrons from this point to the other point there. So I hope everyone is following through, because like almost every page depends on the previous page and the entire presentation for group 5. So this is the electron transfer mechanism. So to my right here, as you can see, we have this figure here. So what you can see is that we have the lower valley and the upper valley, the lower valley and the upper valley. So basically, we're trying to move the electrons from the lower valley to upper valley. And if the process continues, like in a cycle manner, it generates some sort of microwave. We'll get back to that later. So generally, how the electron transfer mechanism operates is when a strong electric field is applied. Yeah? When a strong electric field is applied at the lower valley, electrons in the lower valley gains energy. So once an electric field is reached, the threshold that I was telling you about, once the electric threshold is reached, the electric field threshold is reached, the electrons acquire enough energy to propel them to the upper valley. So in the upper valley, the electrons have a lower mobility due to the high effective mass that we had talked about. So since the lower mobility leads to decrease in current, so since we have a lower mobility here, yeah, then we'll have a decrease in the current flow here as compared to here. So there will be that like kind of like difference. So I think you can remember that I told you that the current voltage relationship in this case is does not follow the V equals to IR relationship, where increase in voltage leads to an increase in current. And I think by now you can tell it's because of the effect, the masses. At the lower valley, the masses is low, so mobility is high. So as the electrons move between the lower and the upper valley, this create a localized region of high electric field called a domain. So what I'm saying here is the domain. If you were to kind of like time this period where you're applying the electric field, you realize that it increases like from, let's say, 1 second, 2 seconds, 3 seconds. Yeah. So at, let's say, 1 second, some electrons have gathered enough energy and they are moving towards that upper valley. So after let's say 1.8 seconds, another batch of electrons have gained as much energy and are moving towards that upper valley. So after let's say 2 seconds, some bunch of electrons will have gained the same, would have overcome the threshold and would be moving towards the upper valley. So that movement is what we call the domain. So the movement of high electric field domain causes oscillation in current, producing a microwave signal. That's actually the basis of operation of the gun diode, the movement of the domains, the one that I've just explained. So we can just read through it for further understanding. So two value models suggest that there are two regions. I think we had gone through it. So I think we'll just go to the electron transfer mechanism. Yeah. So when the, oops, it's okay. So the electron transfer mechanism, I've gone through it, but yeah, I can still go through it actually. So when the electric field is lower than the electric field of the lower valley, then the electrons will occupy the state in the lower valley. So that's the materials in the highest average velocity state, and the diff velocity increases linearly with increasing potential. Obviously, the potential through the electric field. Yeah. So I think you guys can read through the remaining part of it. So when the electric field, as the applied electric, I'll just go to the second part. As the applied electric field is increased, that is like from 2 to 4, higher than the lower valley electric field, and lower than the upper valley. So like in between, like intermediary between the electric field here and the electric field here, in terms of value, that is. Electrons will gain energy from it and move upwards towards the upper valley, as shown in the figure 7.36b. So I think it's this one here. As the electrons transfer to the upper valley, their mobility decreases and their effective mass is increased. Thus, the decreasing in the current density, J, hence the negative differential resistivity. So the negative differential resistivity is that aspect where current does not increase with voltage. So the final case here is when the applied field is higher than the field in the upper valley. So all electrons will be transferred to the upper valley because we've broken the threshold that needs to be overcome for electrons to move from the lower valley to the upper valley. So, yep, I hope you guys are still listening. So So from the electron transfer mechanism and the two-valley theory, the two builds on the Gunn effect. So the Gunn effect, we'll just go through it together. So the Gunn effect is a high-frequency oscillation of electric current that is flowing through the semiconducting solids. As I had said earlier, there's that domain that was being formed from lower valley to the higher valley. So that constitutes the oscillation here. So from the two-valley theory, we've seen that the electrons are present in high mass, low velocity, that's the upper valley, and the low mass, high velocity state, that's the lower valley. So, so when a high electric field is applied across the material, that's the contact that I told you earlier, the electrons in the lower energy valley gain sufficient kinetic energy and begin to transfer to the higher energy valley. In this higher valley, the electrons have reduced mobility. So since it's a charge carrier and we have difference in mobilities between the lower valley and the upper valley, it can tell you something to do with current. The current in the lower valley will be higher than the current in the upper valley. So in this higher valley, electrons have reduced mobility, which reduces the current flow, even though as the applied electric field remains constant. So if we continue applying electric field, we realize that more electrons in that matter, like the domain, is kind of propelled towards the upper valley, but the current relationship does not hold. So that's what that point meant. So the transition of electrons to a state of lower mobility results in decrease in current with increasing electric field, so creating a region of negative differential resistance. I think by now you guys can understand from the repetition of the mobilities and the current relationship that I've been saying. So once the critical electric field is reached, a high field domain is formed and propagates through the material, generating an oscillating current. So I think these are a repetition of what I had explained earlier. So the oscillations generated by the movement of high field domains create a microwave frequency signals. So this actually, in hindsight, this is the application of the gun diode through the gun effect. So for a gun diode to operate, we need the gun effect. Yep. So once we have the gun effect, then we can make this application here, creating a microwave frequency signals. So this will be discussed later on under the applications. So these are the characteristics of a gun diode. As you can see, we have the current voltage relationship. Yeah. So as you can see initially, this depicts the lower value. As voltage is increased, current increases. So the VIR relationship still holds. To after a given threshold is met, that's when the electrons start propelling from the lower value to the upper value. Once that barrier is broken, further increase in voltage does not constitute an increase in current. As a matter of fact, current starts decreasing because of the difference in mobilities. In the lower valley, we had high mobility. That's why we had more carriers moving. And if more carriers are moving, then current is high, right? But in the upper valley, uh, due to high mobility, the electrons are not moving as such as compared to the lower valley. That's why we have reducing current, and reducing current for the V equals to IR relationship, then we'd see that current will be decreasing. So this is exactly what is being shown here. So yeah, we might can as well read through what I'd given you guys here. So and obviously the process continues. So it's kind of like a sine wave. That's why I was telling you about the domain formation after a while, after a while, after a while. Yeah. So characteristics of the gun diode. This is actually an explanation of what's going on in the graph that we have to the right side. So at low electric field, the electrons are moving in the lower valley in the conduction band, which has a high mobility, hence offers positive resistance characteristics. This region here, from the start to the peak point, the blue. So at high electric field, now at high electric field, that means the threshold has been overcome. There, electrons are moving in the higher value. So, and you can remember for electrons to move in the higher value, the threshold needs to have been overcome. So it's anywhere beyond this point. So electrons are moving in the higher value from the lower value in the conduction band, which has lower mobility. Hence, it offers the negative resistance characteristics. Yeah, the V equals to IR relationship. So finally, we have the applications of gun diode. So all these the first application, second, and the third, they all build on this characteristic here, the gun effect and the electron transfer mechanism. So the first application is microwave oscillators. So, okay, I'm not so conversant about these applications because it's something it's actually beyond us. So I don't expect you guys to be asking me more questions, a lot of questions on the application part, because I think it's a specialized area, and as it stands, we are not specialists. Almost there though. So microwave oscillators. So this is the first application. So in microwave oscillators, we have radar systems. So they are used in radar applications for generating microwave signals. As I said earlier, if I can scroll back, I'll show you something. Here, the last point in gun effect, we have the microwave signals that we are talking about. That's the basis of the first application. So they are used in radar applications for generating microwave signals, enabling detection and ranging of objects such as aircraft, ships, and weather formation patterns. I think Sam and Eric knows much about these radar stuff. Sindio Sam? Okay. Yep,
Not
clearly.
that much.
Okay. So the second application is satellite communication. So earth station equipments under that satellite communication. So they are used in ground-based systems for communication with satellites, especially in the microwave frequency bands. So I think some of these things it's somewhat self-explanatory because I'd said we're not specialists. So the last one is medical applications. So microwave imaging under that medical applications. So they can be utilized in microwave imaging systems for medical diagnosis. I think from the book that I had shown you in page one, this book here, the one in blue, it explains more about the applications beyond it. It's actually like almost 3 or 4 pages based on each applications that we had here. So in case you guys need the books, I'll share with the class rep or through the class group, and you can have better understanding of it. Yep. So that's my presentation under the GAN diode. So I think the next one will be impact diode from Adrian. Yeah. So
Thank you. Just a moment.
Yes.
Sorry for interrupting. Finish first, then I'll see what I have to say.
Oh yeah, I have finished. I finished through the application, so I was just going back to the first page. Yeah.
Okay. So there's a presentation that was missed for group 4. We'll have it
Group 4.
first, then we can move on to the impact diode.
So.
Yeah.
Okay. So in case you guys have any questions or anything about, other than that, you can hit me up and we can discuss more. So I'll stop presenting for group 4. Thank you.
Hi, can you hear me?
Yes.
Yes.
Okay, so I have a presentation on application of the signal flow graphs that Kerry had covered. Okay. So we want to look at a specific application regarding calibration of network analyzers, specifically vector network analyzers, which are used for measurement of S parameters. Okay. So as previously discussed, the VNA vector network analyzer measures scattering parameters as ratios of complex voltage amplitudes. The primary reference plane, this was covered by cargo. For such measurements is generally at some point in the analyzer itself. So the measurements will include losses and delays. Phase delays caused by the effects of the connectors. These losses and phase delays can be seen from considering the propagation coefficient gamma that we covered in transmission lines. Okay, so those losses and phase delays may be modeled as two-port error boxes. Two-port error boxes which are placed at each port between the actual measurements, and the calibration procedure is therefore used to characterize the error boxes before measurement of the device under test. Then the actual error corrected scattering parameters of the DUT can be calculated from the measured data. Okay, so this is the block diagram of what I've just explained here. The modeling of the the losses and phase delays as error boxes. You can see here. Port 1 is on the left, right next to reference plane for device port 1 here. Then port 2, reference plane for port 2. Yeah, then the error boxes. Okay. Then the whole setup I'm sure you're familiar with now. The input side with the incoming voltage wave and reflected voltage wave, and the right side with the reflected voltage wave B2, which is the output, and the input of E2 being the incoming voltage wave. Okay. So the simplest way to calibrate network analyzer is to use 3 or more known loads, such as shorts, opens, and match loads. They are commonly referred to as SOLT for short, open, and loaded. but this comes with drawbacks because the standards are always imperfect, introducing additional errors which add on to the losses and phase delay that we've already discussed. Yeah, and these additional errors worsen with increase in frequency. Okay, so the alternative to using the SOLT, the short open and loaded configurations, is using the TRL calibration scheme, which uses 3 simple connections to allow the error boxes to be characterized completely. And the TRL connections are through connection, reflect connection, line connection, as you can see. Okay, so the 3 connection types can be analyzed using signal flow graphs to derive the necessary equations of the scattering parameters of the error boxes, because as you'll see, the whole system can be modeled by overall scattering parameters, but these are not the scattering parameters we need. They are the individual scattering parameters of the error boxes that will be needed. Okay, so this is the general two-port network represented as a signal flow graph. I think this was also covered by Kerry. Okay. Yeah, so this is, now we're about to enter the actual analysis. Yeah, can read through this. Then we shall make some few assumptions. Can assume that the characteristic impedance for ports 1 and 2 of the DUT are equal, meaning, for example, if you have a coaxial or an SMA connector, you assume that for port 1 and port 2 of that same device, you've chosen SMA connectors which are equivalent in characteristic impedance, and that the error boxes are reciprocal and identical. This is just to simplify the analysis. Yeah. So for the first case, we consider the through connection, which is just simply connecting the ports 1 and 2 directly, meaning, as you'll see later, that it's direct transmission. There are no losses due to transmission line or something like that. Yeah. And this is how the block diagram will look like, with the error boxes which are opposite to each other and are reciprocal and identical. So this is the equivalent signal flow graph of the through connection, as I'd mentioned here. This one. So this block here, as you've seen here, this block is the general two-port network. So the error boxes have been converted to the equivalent signal flow graphs here and here. Then in between here is the through connection, the ones which symbolizes that the port 1 and port 2 have been connected directly. Okay, so using the assumptions we had made and noting that the error boxes are symmetrically arranged, which means they're connected on image basis, as I'd mentioned here. You can see the arrows are opposite to each other. We can identify a plane of symmetry here at between 1 and 2, and the error box on the right will be the image of the error box on the left. Okay, I'll skip a bit. Yeah. So, noting those assumptions and applying the principles that Kerry had taught you guys, you'll come to this equation, and noting that the whole system is symmetrical, therefore T11 and T22 are equal. T11 and T22 are the overall S parameters for the through connection, but they're not the S parameters of the error boxes. And applying the same principles of signal flow graph analysis, you find that T12 is equal to this, and by reciprocity, it's equal to T21. Then for the reflect connection, we now use a load which has a significantly large reflection coefficient, which can be considered as a nominal open or short. But this value of gamma L is not really needed, but you can derive it as we will later by using the calibration procedure. So see, this is the circuit model of the reflect connection. So as you can see, port 1 and port 2 will not be directly connected because of the significant reflection coefficient, which results in decoupling. And because of that, you can see here, there will be no transmission between the two error boxes. So the overall S parameters R for this system will not be including R12 and R21 because there's decoupling of the two systems. Okay, that's what I've just explained. Then applying the principles of signal flow graph analysis, you'll find that R11 is equal to this, and R22 is equal to R11 by symmetry. Then considering the line connection, now this is a transmission line which is matched to the error boxes, and as we saw in the reflect connection, we don't really need to know the length of the line or the propagation coefficient because they will also be determined by the Tyrrell procedure. So this is the equivalent circuit model, and here is the line of length L characterized by some propagation coefficient gamma and characteristic impedance Z0, which is matched to the error boxes. This is the equivalent signal flow graph for the line connection, the two error boxes, and the lines. So as you can notice here, if you replaced the through connection with E power negative gamma L, you'll have the line connection by just looking at the signal flow graph. So if we note this, in other words, the E power negative gamma YL has been included to account for losses and phase shift experienced, or what we noted as phase delay. Yeah. So by noting that, you can just replace the one for the T11 and T12 with E power negative gamma L, and because they are two, because of this squared, you get this power doubling, and the same thing happens for L12. Then by symmetry and reciprocity, you can get L22 and L21. Okay, so now we are looking at the evaluation of the propagation factor, E power negative gamma L, and the reflection coefficient. This one was seen for the line connection, and this one was seen for the reflect connection. So I've skipped a lot of things here because the manipulations are too lengthy. Okay. Manipulations are too lengthy. But simply, if you consider equations 1, 2, this one for the T11 and T12, and 4 and 5 for the L12, and L11 and L12, and manipulate them, you can get this equation and this equation, these pair of equations. Then you can note that this first equation 6, can be written as a quadratic equation of S22. Then you solve for S22, and you'll get a function of S22 as a function of L12 and T12. then you plug in that function of L12 and T12, that S22 as a function of L12 and T12 into this equation here. By doing that, you've eliminated all the S parameters of the error boxes, and you're now remaining with the TRL, actually the TL, but the key thing is eliminating the error box S parameters. Now after you do that, because in this case we want to evaluate the coefficient, the propagation coefficient and length, which you'll get by considering this e power negative gamma L. So because we want to do that, and we have one equation only composed of e power 2 gamma YL, gamma L, T11, T12, and L12 and T12, you can now notice that you'll also get a quadratic equation in terms of e power gamma L. So e power gamma L squared is e power 2 gamma L, and that can give you a quadratic equation. And solving that quadratic equation gives you a closed form for e power gamma L. And this is what is explained here. So for determination of gamma L, this is now capital gamma L, the reflection coefficient. We now still consider the T11 equation, the T12 equation, the L11 equation, and the L12 equation. By considering that and manipulating it, you can get these three sets of equations. And now, conveniently enough, if we look at the reflection coefficient, we have the only things we have are S11, S12, and S22, which are not required. So if you write gamma L as the subject of this formula, then as you've seen here, we have equations of S11, S22, and S12 in terms of the S parameters of the TRL variables. You now see that we can now plug in S11, S12, S22, and S11 as seen in these equations, and you'll have gamma L completely characterized by the TRL parameters. And now that has shown that this has been satisfied, these two things. First thing is that the length is not needed to be known, and the reflection coefficient is not needed to be known. And now that you have those, you have everything you need to completely characterize the device under test and eliminate the loss and phase delay errors that were troubling us before. Yeah. So this is the reference, Microwave Engineering by David M. Poser. Yeah. And thank you for your attention. If you have any further questions, feel free to reach out. This is my email, and those of you who have my number can also text me. Thank you.
Thank you. So we'll go to the next presentation for group 5 next week, since I see there's only 5 minutes left. Or would you want to present now? Then you can continue next week.
I think next week will be appropriate.
Okay. So we'll start with you next week. We're done for today. You can leave the meeting.